Hey everyone, welcome to the hands-on session on TensorFlow. Now, as we progress in today's session, you'll understand what is deep learning. So we'll have a short introduction to deep learning. We'll understand more about this TensorFlow library. And then we'll take up a case study where we are going to build a classifier using a TensorFlow. And at the end, we are going to implement it in a hands-on manner. So this is a complete end-to-end tutorial on TensorFlow. So stay with me till the end to learn more. So let's get started. Let's start by understanding what is this deep learning. Now, when I talk about this deep learning, so this deep learning is a subset of machine learning. Now here, this deals with the analysis of the data, but for performing this analysis, we are going to make use of a structure which is inspired by a human brain, which is actually called as artificial neural networks. So using my artificial neural networks, I'll be analyzing my given data set so that I can find the patterns that is present in my given data. Now, while working with deep learning, obviously any learning journey will begin by understanding about perceptron. Now, perceptron is a very simple model, guys. So I can say perceptron is one of the building blocks of my deep learning. So this perceptron was actually invented by Frank Rosenblatt in the year of 1957. Now, what this person has done is he just tried to simplify the mathematical model so that we can simulate the way that we work in human brain. Now, this is the simple representation of perceptron. In my perceptron, I have the various inputs. Let's assume I have n features with me. X1, X2, X3, up to I have Xn. So I have n features with me. And each of this feature will carry a weight with them. So these weights represents the importance of these features. Now, here along with this features, it also has a bias for that specific perceptron. Now here X naught is actually called as bias term, and overall this W naught is a bias term. X naught is simply to mention that we are going to perform the mathematical operation without any issue. So W naught is my bias term. W1, W2 up to Wn refers to the weights for each and every individual feature. Now inside this perceptron, two things will happen. One is a summation. The another operation that happen over here is called as activation. So this is my activation. Now in the scenario of summation, what I'm actually going to do is I'll take the dot product between my weights along with my inputs, that is my input feature. So I'll take the dot product between my weights and my input, and then I'm going to apply it on top of my activation function. So which is nothing but if I try to expand the summation notation, it will be given by x0 w0 plus x1 w1 plus x2 w2 up to xn wn. So this is how the summation operation will happen. And now on top of this summation outcome, I'm going to apply an activation function. Now in the scenario of perceptron, it's a very simple activation function. I'm going to set some threshold, okay, or I can simply say the threshold can be simply saying as 0. So it clearly says that if I have the value of summation, if it is greater than 0, then I'm going to determine the value of output as 1. If I have the value which is less than 0, then I'll determine the output as 0, which means this perceptron is able to classify my given data into either one of the classes, that is either 0 or 1. So this is the working of perceptron model. Now, as you can clearly see, it's a very simple model. It just takes in the inputs and the weights, and then we'll perform the summation. On top of it, we'll apply a simple activation function, and whatever the outcome that I'm going to get, I'm going to check if it is greater than 0. If yes, I'm going to say that the class output will be 1. Else, I'm going to say that the class output will be 0. It's a simple binary classification problem. Now using this perceptron, just remember we can solve the problems which are like OR, AND, but we cannot solve the problems like XOR. So I can solve the problems like OR, see? Or I can solve the problems like AND, but I cannot solve the problems like XOR. So this is one of the disadvantage that we have when it comes to the perceptron. Now what happened? So the people and the researchers, they started increasing the complexity of model. Now, as they started increasing the complexity of model, what they actually did is instead of having a single perceptron, let's arrange in such a way that we are going to have multiple perceptrons, and we'll have such multiple perceptrons in each and every individual layers, and that brings us to the concept of hidden layers. So this is the representation of my hidden layers. Now, this is the overall output or the overall representation that you see over here. This is called as multi-layer perceptron. Now here in this multi-layer perceptron, I have multiple hidden layers. And in each hidden layer, I have multiple perceptrons. So which means each and every circle that you see over here inside each and every hidden layer, so each and every circle represents my individual perceptron. Okay, so these are my individual perceptrons, and I'm arranging these perceptrons in such a way that it is span over multiple hidden layers. So as a result of this, my input is able to go through multiple layers, and because of this facility of having the multiple layers, I'm able to understand some of the complex representations for a given data. And that's one of the advantage of having this multi-layer perceptron architecture. And this multi-layer perceptron architecture is also called as deep learning neural network. Now the question that you might have is, hey, what is happening inside each and every neuron or each and every perceptron that is happening or that we have in this multi-layer perceptron? So in each and every circle that you see over here, two things will simply take place. One is a summation and the another one is activation. That is very common. So the only difference is we have multiple perceptrons in each layer, and we have multiple layers. So that is what we call it as a deep learning neural network. Now with this deep learning neural network, we can also implement the problems like XOR, that is XOR, which we were unable to do it with the help of a single perceptron. Okay, we'll have an architecture like this, and we are going to have this output layer. Now this output layer will give us the output from this deep learning neural network, and through my input layer, I'm going to receive the input. Now what happens when we have these kind of layers is we are going to perform the training. Now in order to perform the training, we make use of a technique that is called as backpropagation. Now the way this is going to work is I'm going to get some data set. So I'll have a large volume of data set which will be with me, which I'll be using it to find the representations in a given data set. For example, if I'm building a classifier or if I'm building a deep learning model to detect whether my given image contains a dog or not, then my data set will contain large volume for images of dogs. So it will contain large volume for images of dogs. Now using this large volume of images of dogs, I'm going to train my deep learning model. So I'll train my deep learning model. Using my deep learning model, I'm going to find the patterns. Now when I say training, what happens is during the first phase, I'm going to initialize all my parameters to some random values, and I'm going to make a forward pass. Now, when I say forward pass, I'll send my data, that is, I'll send my input through each and every layer that we have over here. I'm going to send my data through each and every layer. Now, once the data passes through each and every layer, at the end, through my output layer, I'm going to generate the output. So if I generate an output, that will become one forward pass. Now with that outcome of this forward pass, I'm going to check whether the prediction or whether the output that I'm getting from my model, whether it is correct or not. If it is correct, then I'm cool. If it is not correct, then I'll make use of the concept of gradients, and I'm going to update the parameters in my deep learning model, which means I'll go in a backward way to update each and every parameter in my deep learning neural network. And this concept is called as backpropagation. In order to perform this backpropagation, I'll make use of the value of loss. And for this value of loss, I'll find the value of gradients with reference to each and every parameter such that I can determine how to update each and every parameters in my deep learning neural network. Now, once the model is trained, yes, once the model is trained, I'll choose a similar kind of data which I have with me so that I'm going to perform a forward pass and I'll generate the prediction. So this is the overall process of training my deep learning neural network. Now, TensorFlow, which is a topic of this video, will use this TensorFlow library to create such deep learning neural networks and perform the training. So let's understand what is this TensorFlow. Well, guys, if I want to put it simply, TensorFlow is an open source library for numerical computation using data flow graphs. And this TensorFlow is developed by Google Brain team to conduct the machine learning research. And this TensorFlow is actually an interface for expressing the machine learning algorithms and an implementation of executing such algorithms. If I want to quote from the TensorFlow's official documentation page, I can say this TensorFlow is an end-to-end open source platform for performing the machine learning. Now, this has comprehensive, flexible ecosystem of tools, libraries, and community resources that lets researchers push the state of the art in ML and developers easily build and deploy ML-powered applications. Now, the benefits of using this TensorFlow is obviously easy model building, which you are going to see as you progress in today's session, and robust machine learning production model everywhere, and then powerful experimentation for research. So these are some of the important benefits when it comes to TensorFlow library. So we have just seen right now what is deep learning and how does the changes will happen when I send in the data through this deep learning as well as perceptron. Now, if I want to simply implement it with the help of TensorFlow library, then the programming of this forward pass would look something like this. Here I have the data which is X. Okay, so this is the data which is X and I have their respective weights that is W. Now we also have this bias term that is P. Now what happens in the first step? In the first step, obviously as we know already, we are going to take the dot product between my inputs and the weights term. Now in order to represent this dot product, here I can say that it's a matrix multiplication. So I'll perform the matrix multiplication with W and X. And then whatever the outcome that I'm going to get, I'm going to add my bias term. So this overall step that is matrix multiplication and adding the bias term will be in total, I can call it as a summation. On top of this, I'm going to apply a function which will help me to scale the values in a required range. Now here in this example, I'm applying the function of ReLU, which is one of the activation function, which helps me to scale it such a way that I'm going to get only the positive values as an output. Okay, so this is the working of this overall programming model or in this overall equation. I'm applying this ReLU activation function on top of the dot product between my weights and the inputs plus my bias term. Okay, here I have just splitted the overall operation into multiple substep, guys. The reason because when you do these kind of operation in TensorFlow, this is how the TensorFlow is going to remember each and every operation that you are going to do. If I want to completely break down what is happening and how we are going to train and represent these kind of parameters, while working in this TensorFlow library, we will be working with variables. Now variables are nothing but the stateful nodes which output their current value. Okay, so these are called as my variables. Now here in this figure, W and B, so W and B are the variables in this given example. Now with this variable, what it happens is its state is retained across multiple executions of a graph. Okay, so these are the variables. So whenever I'm having any parameters in my deep learning neural network, I'm going to define it as a TensorFlow variables. Okay, so when I say these variables, these are stateful that they retain their current value over multiple executions. Now here they have more number of usage when it comes to variables, guys. So the reason is like whenever we are training any deep learning model, we will be using these variables. Now using these variables on top of it, I'll be able to compute the gradients, and using those gradients, I'll be able to update my variables. So that's the advantage of working with variables. Now apart from variables, we'll also be working with what we call it as placeholder. Now, placeholders is nothing but the nodes whose value is fed at an execution time. Now, here in this scenario, the X is actually called as a placeholder. Okay, now when we talk about this placeholder, so here in case of placeholder, this placeholder has the initial assignment. And normally the X in a general scenario, my inputs and the labels will be represented as a placeholder. So variables and placeholder is what we'll be using it, and on top of it we are going to apply this mathematical operation, that is matrix multiplication, addition of my element wise, and then applying my activation function. Now, if I want to hard code it with the help of TensorFlow library, this is how my code snippet would look like. So here in this scenario, I'm importing my TensorFlow as TF. I'm defining two variables W and B, and then I'm creating my X as a placeholder, and I'm defining my H, which is nothing but the overall output from this model, which is nothing but tf.nn.relu. So I'm applying the relu activation function on top of the matrix multiplication of X and W and performing the addition of P. Now, this is how we used to code in a previous versions of TensorFlow. Now the best part is with the latest addition of TensorFlow 2.x, so it has been simplified, guys. It has been simplified such a way that we have the set of APIs that is available under the Keras module. So we'll make use of Keras API, and that actually makes our life easy whenever we are writing the deep learning neural networks. Now let me show you how do we actually write something when we are using this Keras API. So this is a demonstration as how do we create a model with this Keras API, and throughout our learning journey in this video we'll make use of Keras API because that's one of the best way to learn this TensorFlow. So in order to work with this Keras API to create a model, first we'll initialize the model. Then like before we initialize the model, we'll import this TensorFlow as TF. Then here I'm initializing my model as sequential. Now, once I define my model as sequential, I can go ahead and specify how many number of layers that I want as per my requirement. And while specifying, I can mention what will be the activation function. I can specify what will be the shape, that is how many number of neurons that I'll have in each layer. And along with that, I can also mention the activation functions as well. So we have various activation functions that are supported by TensorFlow. Some of the important ones are softmax, sigmoid, tanh, and relu. And once we define the model, the next thing that we have to do is we'll have to compile the model. So we'll say model.compile, and inside the parenthesis, we'll have to specify the optimizer. This optimizer is responsible for updating the parameters in my deep learning model. So we'll specify the optimizer, we'll specify the loss function, and we'll also specify the metrics, that is the way in which I'll have to evaluate my models. Now, by specifying all these things, we'll complete the compilation step, and then we can go ahead and call the fit method to perform the fit for my input and the output data. Now, in order to understand everything in detail, we'll take up a case study. Now, the case study that we are going to consider in this video is handwritten digit classification using TensorFlow 2.x. Now, as part of this case study, so we are going to perform the following task. So we are going to get the data set, we'll install the TensorFlow, we'll implement the perceptron on this data set, then we'll train the perceptron and we'll evaluate the perceptron. And after that, we are going to implement the deep learning neural networks. And finally, we are going to try to optimize the model that we have built. So these are the tasks which we'll be performing in our hands-on session. Now, as I mentioned, we are going to make use of a data set, which is the classification of handwriting. Now, this data set is actually called as MNIST data set. So this MNIST is actually an acronym which stands for Modified National Institute of Standards and Technology data set. Now, this is a data set where I have 60,000 small square 28 by 28 pixel grayscale images of the handwritten single digits between 0 to 9. And on the right hand side of the screen, you can see how does this sample images would look like. So what we are going to do is we are going to make use of these images that we have with us. We'll make use of these images and we'll try to classify them. That means if I send any image, for example, if I write something like this and if I give it to my deep learning model, I want my deep learning model to identify what this image or what this representation is going to tell me. So what is the number it represents? It represents the number 4. So that is what I'm trying to build right now, which is a handwritten digit classifier. So let's get started and let's go to the Google Colab and let's start coding. I'm now in Google Colab, so let's get started. Now, here when we are working with this Google Colab, this comes with TensorFlow pre-installed. But in case if you want to install the TensorFlow library, just run the command pip install TensorFlow. So this is going to install the TensorFlow library in your current system. So here in this scenario, as I mentioned, this Google Colab comes with pre-created or pre-installed TensorFlow, so we don't have to install it again. Okay, so it says it has updated to some nightly version. That's still fine for us. Okay, once the installation is complete, the next thing that I'm going to do is let's import it and let's validate whether the installation is completed or not. I'm going to say import TensorFlow as TF. Okay, that's the shorthand notation that I'm going to use. Now once imported, I'm going to display the version tf dot underscore underscore version underscore underscore. If I execute this, this is going to display the version of TensorFlow that is currently installed. So the version that is currently installed in my current session is 2.8, which is the latest version right now. That's amazing. So let's get started. Now the first thing that we are going to do is we are going to get the data. Now in order to get the data, this MNIST dataset is available inside the TensorFlow library itself. So in order to load the data, I'm going to call something like this. I'm going to say MNIST is equal to tf dot keras dot datasets dot MNIST. So this is going to get the data from the TensorFlow server. Okay, now once this is done, so once this MNIST object is created to load the data, okay, in order to load the data, we'll have to call the load data function. Now, once I load the data, it is going to load the data in terms of tuple. So as a result of this, I'm going to say xtrain, comma, ytrain, okay, and I'll say xtest, comma, ytest is equal to MNIST dot load underscore data. Now, once I execute this, this is going to get the data from the TensorFlow server and it is going to load it as a tuple separately for my training data as well as my test data. Now, let's go ahead and explore the shapes of the training data that we have just loaded. I'm going to say xtrain.shape and I'm interested to understand the xtest.shape. So the shape of my training data is 60,000, 28 by 28. And my test data is 10,000, 28 by 28. So 10,000 rows, that is 10,000 images for my training data. And I have 60,000 images for my test data. That's great. And here 28 by 28 represents the shape of my individual image. Now the next thing that we are going to do right now is we are going to pre-process the data. Now, the reason that we want to do the pre-processing because here in this scenario, okay, let me say max. Okay, if I say max and if I send in my xtrain, okay, it is going to give me the output. So, okay, let me do one thing. I'm going to say np.max. Let's call the np.max. And for that, I'm going to load my NumPy library. Now, I want to show you what is the maximum value over here. The maximum value in this xtrain is 255. Now, when I display the minimum value is 0. That means I have the values ranging between 0 to 255 in my training data. And the same thing is applicable on my test data as well. For example, np.max, and if I mention as test, and if I repeat the activity and display the minimum value for my test, okay, just observe both for my training data as well as test data, the maximum and the minimum value is 255 and 0 respectively. Now, what we can do, we can normalize this data. Now, when I say normalization, we can ensure that instead of falling in the range of 0 to 255, we are going to divide by 255 so that we can get the output in the range of 0 to 1. Now, in order to do that, Let's do one thing. Let's convert this xtrain and xtest data into the floating point, and then we can go ahead and normalize it. The way that I'm going to do is I'll simply say xtrain is equal to xtrain dot as type, and I'll specify the type as float 32. Okay, and I'll repeat the same activity for my test data as well. Okay, so in this way, I'm changing the values to the floating point numbers. Now, once this is done, I'm going to convert it in the range of 0 to 1. In order to do that, I'm going to say x train is equal to divide is equal to 255. Okay, and I'll repeat the same activity for my test data. So this will take care of normalization. Okay, now once this is done, let's check the maximum and the minimum value again. So I'll copy over here. We'll add everything in a single cell. So the maximum values now are 1 and the minimum values are 0. So we have done the normalization. Okay, now one common practice that we do whenever we are training any deep learning model is we have to send the data as a flattened vector, which means I'll have to convert my multidimensional array into a single dimensional array before I start training it. But here if you observe, if I display the shape again, that is xtrain, my xtrain is having the shape as 60,000 comma 28 by 28. So my each and every individual instance of my data set is having the shape as 28 by 28. Now, as part of next pre-processing technique, I'll be converting this 28 comma 28 into 28 multiplied by 28. So let me tell you what it means. I'm going to say new shape, okay, new shape is equal to, I'll write as 28 into 28. So what it means, my new shape is now value will be equal to 784. Now what I'm going to do right now, I'm going to reshape this xtrain. So I'll say xtrain is equal to xtrain dot reshape, and I'll reshape it to the shape of 60,000 comma new underscore shape, and I'll repeat the same thing for my test data as well. Okay, I'm reshaping my test data, but instead of 60,000 in my test data, I have 10,000. So 10,000 comma new shape. So if I execute this and now display the shapes of my training data and the test data, so we'll be able to see that this time we have flattened the input data. So previously our input data in the dimension of 28 by 28. Now it has been converted into a one dimension representation. Okay, so this takes care of the important things that we have to worry while working with the data, that is preparing the data and pre-processing the data. Now, another thing that we have to do right now is we'll have to take care of the output data. So we haven't seen what is this output data is containing, isn't it? So I'll say ytrain, and if I display first few rows of this ytrain, so my white train is having the values like this 5, 0, 4, 1, 9, 2, 1. So what it represents is it is going to represent as what is the digit that my given image would belong to. So this is how my data set is. Now, as part of our pre-processing, now what we are going to do is we are going to convert the output data, that is y data that we have, into a one-hot representation of the labels. Now, in order to do the same, I'm going to say ytrain is equal to tensorflow dot keras dot utils dot to underscore categorical. So we have a function that is called as to underscore categorical, and I'll specify my ytrain. Okay, and the number of classes that we have in the given data is 10, so I'll mention as 10, and I'll repeat the same thing for my y test as well. Now once this is done, I want you to observe the shape of the y train. Now before I do that, if I display the shape of my y train, and I'll also display the shape of my y test as well, so that you'll have a clarity. So my y train is of the shape 60,000 comma blank, that is it's a single dimensional array with each label for my each and every image, and for the test data I have 10,000. So 10,000 labels which each with each data for my individual image. Now once I convert it into the one hot representation, if I now display the shape of my white train, so white train dot shape, so this now has the shape as 60,000 comma 10, which means we have converted my individual value into a one hot encoding vector which has the length as 10. Okay, so this is what we have done right now. Now, what does it actually mean? It means I have converted into one hot representation. Now, let's do one thing. Let me just display one of the value in my white range. So I'm going to pick a first value in my white range, and let's see how does the data is represented. We have everywhere as 0 except this place. So let's count the index position: 0, 1, 2, 3, 4, and 5. So in place of fifth index position, I have the value as 1. Now let's do one thing. Let's create a visualization of the first image that we have in training data, and let's see how it would look like, whether it looks like 5 or whether it looks like any other number. First, I'm going to import the matplotlib. So import matplotlib dot pyplot as plt. So I'm importing this pyplot module. Now once this is imported, next I'm going to call this function plt.imshow. Okay, inside the parenthesis, I'm going to get one of the image from the xtrain, so xtrain 0, and I'll have to reshape it to the shape of 28 by 28. Remember guys, the reason that I'm doing this reshape because here I have already flattened my given data. I have already flattened it. So in order to ensure that we are going to get the display as an image, I am reshaping it to the shape of 28 by 28. Now after that, I'll simply say plt.show, and if I execute this, see, we have the image and this is how it would look like. This clearly looks like the digit 5, which is same is being conveyed in my white train. So which means I have the labels present in my white train and I have the data present in my X train. Now that we have pre-processed the data and we now know how the data would look like, let's get started and let's build the model. Now here to get started, first I'm going to build a very simple model, guys. I'm going to build a very simple model, and in this simple model I'll just have a perceptron kind of scenarios. So let me show you how I'm going to create a model. Now in order to create the model, I'll define my model as sequential. So in order to define my model as sequential, let me import the sequential first from TensorFlow dot keras. I'll import my sequential. Okay, and along with that, while defining the layers, okay, so we are going to define the layers as dense layers. So I'll import the dense layer as well from TensorFlow dot keras dot layers import dense. Okay, so this will take care of importing both sequential as well as dense. Now, once this has been imported, I'm going to define my model. Model is equal to sequential, which means I'll be adding the layer one next to each other. So that is the meaning of the sequential model. Now, once I define it as sequential, I'm going to add a layer. So this time I'll simply add a single layer, model.add, and I'll create it as a dense layer. It will have 10 neurons, and the input shape, that is input underscore shape, is equal to my 784. That's the shape of my individual image that we are getting. I'm just going to specify a name. I'll specify a name as dense. Okay, and here I'll specify my activation is equal to softmax. Okay, now let me help you break down what is happening. So this, I'm initializing the model as a sequential, which means I'm creating a model where I'll be stacking one next to each other. Okay, and here in my first layer, I'm having 10 neurons. So that is what it means. So I'm having 10 neurons over here. That is what this 10 represents. And the number of inputs that I'm getting over here is 784. This is the number of inputs that I'm receiving right now. And in each and every layer, I'm having the activation of softmax. So this is the meaning of this sentence that I have just written. Now I'll just execute this, and this is how I'm going to create a model right now. This is my first trial of creation of model. Now once I create this model, I'll just perform the compilation. In order to perform the compilation, we'll have to specify the optimizer, that is the learning algorithm. We'll have to specify the loss function as well as the metrics. So I'm going to say model.compile, and inside the parenthesis, I'll specify my optimizer is equal to SGD, that is stochastic gradient descent. I'll use the stochastic gradient descent model, and I'll specify the value of loss as categorical sparse categorical cross entropy in this scenario. Okay, and then along with that, we'll also specify the metrics. So I'll mention my metrics as accuracy. Okay, so this is how I'm going to compile the model. Now, optimizer is going to decide how the parameters in my model will be updated. Loss function is the loss function that I want to use to train my model, and the accuracy is how my model has to be validated after each and every training process. Now, if I display my model summary, that is model.summary method, so it's going to display the overall summary of my model. So how my model would look like. I just have a single dense layer, and it is having the shape output shape as 10, and the total number of parameter is 7850. So this is the overall parameters that I have to train once I perform the training. Now, once the model is created, I'll go ahead and I'll simply say model.fit. And here I'll pass in my training data, xtrain and ytrain. And along with that, we can specify the batch size. So I'll mention my batch size as 128, and we'll specify the epochs as 80. And let's do a validation split. I'll mention my validation split as 0 0.2, which means as it proceeds in the training, it has to split my training data into two parts. One part, that is 80% of the data, will be used for training purpose, and then remaining 20% of the data will be used for evaluation purpose. I'm going to assign it to an history object. The variable, I'm going to call it as history. I'm assigning over here. Now I'll just execute this cell, and this is going to start training my deep learning neural network. So it is training with the help of my xtrain and ytrain. Okay. Now if you look at it, so in the initial phase, the accuracy that I'm getting on my training data is 65.76, and the validation loss is 0.89, and the validation accuracy is 82.81. And as and when the training proceeds, you can see how the accuracy is getting increased. So 0.8992 and then 0.9081. So the accuracy is being increased as the number of epochs is going to increase. So this is how we are going to train our deep learning model. Now let it continue to do the execution. Now in parallel, let's write the code so that we can visualize how the training is happening. Now in order to visualize how the training is happening, so I have already imported the pyplot module. Now what I'm going to do is I'm going to display the keys that we have right now. I'm going to say print, okay, from this history. So we'll have a history, and this is a dictionary object. And from this dictionary object, I'm going to display the keys. Now what I'm going to do is from this history case, that is from this history object, that is dictionary object, I'm going to plot my accuracy versus my validation accuracy. So plt.plot, and I'm going to plot this history.history, and I'm interested in the key which is equal to accuracy. Okay, and I'll create a plot for my validation accuracy as well. So this is my validation accuracy. Now let's validate it whether it's correct or not. History.history.keys. Yes, loss, accuracy, validation, loss, and validation accuracies. Now this is looking good. I'm going to add some title. I'll add a title as plt.title, and I'll mention the comments as model accuracy. And then I'll add some X label. X label is nothing but my epochs, and my Y label is nothing but our accuracy. Okay, now once this is complete, I'm going to say plt dot show. So this will show the overall display, guys, how the model has performed during the training. So the blue line talks about the training accuracy and the orange line represents my validation accuracy. So this is how it would look like. Okay, now to get the better understanding, maybe we can also add the legend as well. I can say label is equal to train, and I'll mention my label is equal to val, and then I'll also add plt.legend. Okay, so this is how the visualization would look like. Now we can go ahead and perform the visualization on our loss function as well. So instead of mentioning it as accuracy, I'll have to say loss and val underscore loss. Okay, so it's a model loss. So the y label is actually loss. Now, if I execute this, this is how the value of loss is being decreased as the training progresses. Okay, now once we have trained the model, we'll evaluate the model on our test data. Now, to perform the evaluation, we have an evaluate method. I'll mention it as test loss, comma, test accuracy is equal to model dot evaluate, and I'll specify my x test, comma, y test. Now, I'll display my test loss and I'll display my test accuracy. So the loss that we are getting on the test data is 0.396 and the accuracy that I'm able to reach on my test data is 91.83% of accuracy. That's amazing, isn't it, guys? Now let's see and let's get the configuration of the model which we have built. Now, what we have done right now is we have trained the model, we have compiled the model, and once everything is done, we have also evaluated the model. If I want to display the model configuration, the way that we can do is we can simply say model.getConfig. So this is a method that we can use to get the configuration of the model that we have built. So we have the various layer. So first we have an input layer and it takes the input of 784, and we have a dense layer. It has the activation of softmax and it takes the input as 784. So these are all the various configuration that has been set automatically, which are the default values when we create the model as a sequential model. So this completes the implementation of a perceptron on this task of multi-class classification. Now, being this a multi-class classification, since we have the total number of unique classes that we have in a given data set is 10, because of this reason, we have defined the number of units in my layer as 10. Now, apart from that, here I have mentioned my activation of softmax because we are dealing with the task of multi-class classification. Now let's go do one thing. Let's go ahead and let's create a multi-layer perceptron. Now in order to create a multi-layer perceptron, we'll just have to add multiple layers. Now this time I'm going to build the layers like this. I'll say model underscore one is equal to tf dot keras, or yeah, we have already imported, right? So I can simply say sequential. So this is a model which I'm also creating it as a sequential model. I'll say model underscore one dot add, and I'll call my dense layer and I'll have 64 neurons as an example. Okay, and I'll specify my own name. I'll mention my name as dense underscore one, and I'll input shape. The input shape is of the shape 784. Okay, and this time in my first hidden layer, I'll make use of the activation as ReLU. Now, after I add this layer, that is after I add this dense layer, the next thing that I'm going to add is I'm going to add one more layer. Okay, so I'll copy this and I'll paste it over here. I'll mention the layer name as dense2. I don't have to specify the input shape. I'll keep the same activation function, that is ReLU. Now, at the end, what I'm going to do is I'm going to add a final layer, and this will be my output layer. I'll call the layer name as output. Okay, and I'll use the activation, which is the same activation function that is called as softmax, which we have used last time. Now, after that, I'm going to display the model summary. Okay, so this is how the overall model summary would look like. Now, with this simple three-layer deep learning model, we have more than 50,000 parameters. That is the total number of training parameters that we have to train. Okay, this is how my model would look like. Now, here, let's go ahead and print the model or plot the model. Okay, tf.keras.util.utils.plot underscore model, and I'll specify my model underscore one. So this is going to create a plot for the model. So this is how the overall model representation would look like. I have my input layer, I have a dense layer, this is followed by another dense layer, and this is followed by my output layer. Okay, so we have the data with the required layers. Now, once we have the model created, we'll just have to go ahead and do the compilation step. So it's the same process, guys. It's always the same process. We'll define the model, we'll create the model, and then we are going to compile the model, perform the fit, and evaluate the model. And after that, generating the visualization to see how the model is performing. So let me just go ahead and do the compilation. So model underscore one dot compile, and here I'll specify my optimizer is equal to, I'll use the same optimizer, that is stochastic gradient descent, and the loss function is same, that is cross, sorry, it's categorical cross entropy, and then I'll specify my matrix, which is my accuracy. And once my compilation activity is complete, I can go ahead and perform the fit. So in order to do the fit, I'll use the same code which we had written last time. That is the same fit method. Okay, I'll just come below and I'll paste the same and I'll let it train. Okay, so we'll paste it over here and let the training would complete. Now this system has started the training. Okay, so I have let the model for training. So let's let that model to train. So once the model training is completed, we can go ahead and again create the visualization and see how it would look like. So still it is getting trained. So in parallel, I'll just copy the code which we have written last time to plot the model accuracy. And along with that, I'll also plot the loss values. So this is the value of loss. Okay, so let's wait, and once it is trained and once we create the plot, we'll go ahead and evaluate as well. So this time I'll say model.evaluate and we'll specify our x test, comma, y test. And here it's actually model underscore one. So let's wait for the execution to complete, and once the execution is complete, we'll be able to see all the results, guys. So we have completed the training up to close to 70 epochs, and by the end of 70 epochs, the accuracy that I'm getting is close to 92%, and the accuracy that I'm able to see on my validation data is also 92%, which is better than what we had got with a single layer of perceptron. Okay, so the execution has been completed. So this is how the accuracy of my training and the validation data would look like. So my validation data is still working in a better way, and the overall reduction in loss as well as the number of epochs progresses. And here the accuracy that I'm getting over here is somewhere around over here. Yes, so here in this scenario, we can observe that the accuracy that we are getting on this data is 0.1127, which means this clearly is performing the overfit on a given data set. Now, which means we'll have to do some kind of tuning on this model to reduce this overfit. Now, the way that we can reduce the overfit is by ensuring that we are going to add a dropout layer. Now, in order to add a dropout layer, I'll give you a demonstration and how we can do it. So adding the dropout layer is one of the common strategy that we are going to follow while working with deep learning model, because deep learning models are prone to overfit. So we want to ensure that that will not happen. So what I'll do is, after each and every layer that I'm going to add, I'll say model underscore one dot add dropout is equal dropout of 0.3. So I'm going to add a dropout layer after each and every dense layer. Okay, so I'll add my dropout layer. Now, along with this dropout, I'll have to import this. So from TensorFlow dot Keras dot layers will import dropout. Okay, once this is imported, we are adding a dropout layer, which is an additional layer, which will help me to reduce the overfit. Now, once this is done, let's go ahead and compile the model and perform the fit again. So I'll perform compilation and the fit in a same cell so that we will be able to see it's working. So I'll copy this code. And just remember, guys, I believe I did not train it on a new model, guys. I think I trained it on a previous model itself. Let's update it and let's retrain it. And then we'll also add the dropout layers again. Okay. So first things first, let me build my previous layer, model 1 sequential. Okay. Model 1 compile, model 1 fit, and then we'll retrain the model and then model 1 evaluation. Now after that we are going to again build the model, we are going to compile the model, and we are going to fit the model. Okay, so this is what we are going to do right now. So currently we are training two models. So models underscore one dot fit. So let's wait for the execution to complete. So this time with the correct model configuration, guys, so we are seeing the accuracy which is closer to 97%, and the validation accuracy is also closer to 96%. So which means the model one, the latest model which we have configured, so that is performing really well on this data set. And let's see how its performance including the dropout layer. Okay, we are now almost at the end of the first model which we have created. Okay, so let's go ahead and visualize how the model is being performed when we create the plot for model accuracy. So this is how the overall visualization would look like for my training accuracy and the validation accuracy. This is performing well, and this is for the training loss and the validation loss. Next, coming to the evaluation. So we are getting the accuracy of 96.44% accuracy on the test data. That's amazing, guys. Now here I am creating a dense layer. Okay, so dense layer along with adding my dropout layer, and let's see how is the accuracy that we can get. Let me just retrain it. Yes. So let's go ahead and see how the model accuracy that we can achieve by adding this dropout layer. Now, after that, we are going to evaluate the model. Okay, so here I'm doing the evaluation. Okay, we are almost at the end of this training. So we are now at the 80th epoch. Now at the end after the training, we are able to get the accuracy of 96.54% of accuracy on the test data on this optimized model. So what we have done in this video is, in this video, we have learned about what is deep learning, and we have learned how to create a neural network using TensorFlow framework. And we have built the model, we have built with the help of perceptron, and then we have made use of multi-layer perceptron. And after that, we try to optimize the model by adding the dropout layer. So with this, we come to the end of this video on hands-on tutorial with TensorFlow. I hope you guys enjoyed it. I look forward to seeing you in the next session.